All right, so let's do this together. All right. So the first one, we want to get the probability. So again, we're choosing a card, right, from a standard deck of 52 cards. You know, we've gone over what's in that. And we want to know, and then we're choosing another card. So we want to find the probability both cards are from the suit of hearts. Okay, well, we're going to let A be the event. The first card is from the suit of hearts. B is the event that the second card is from the suit of hearts as well. Okay, so we have our events A and B, and we want this, right? The probability of A and B. Okay, well, remember each suit has 13 cards in it, right? So initially there are 13 hearts in the deck. So the probability of A would be 13 out of 52. Okay. What about the probability of B given A? Well, we know that when you choose the first card, there's one less heart and one less card. So we get 12 out of 51. Right? So because of that, the probability of A and B, that's going to equal to this product, which is, of course, this here. Hopefully, it's easy to see before this that the two events are not independent. I mean, it should be easy to see that. I mean, we have this, but if you were to calculate the probability of B, given that A has not occurred, right? That would have been, well, if the first card we chose was not from the suit of hearts, there would be 13 hearts left, but there still is one less card. So we would have 13 out of 51. The probability of B given that A has not occurred. So in other words, I didn't show it, but it should be easy to see that the events, they're not independent. It's really just like the bag of marbles idea. You know, it wasn't independent because we didn't put the first marble back. It's the same idea with the deck of cards. So anyway, we get this. Okay. Are there any questions on that? I mean, I probably should have written down that the events are not independent and actually calculated as well. The probability of B given that A has not occurred. I can always add that later. Okay. But I mean, hopefully you can see that the events are not independent. Again, it's similar to the bag of marbles idea. Okay. Now, what about both cards being aces? Well, it's the same idea actually, except instead of 13 possibilities, right? There's only 4 possible aces though. So it's really the same exact idea. In this case, A, the event that the first card is an ace, we're going to call that event A. Let B be the event the second card's an ace. And again, we want this. But again, just like the first one, these events are not independent, right? It's similar to 1 here, mostly because we're not putting the first card back. The probability of A then would be 4 out of 52, right? There's 4 aces in the deck. The probability of B given A is 3 out of 51 then, right? Again, for A, that's the probability here. This is the probability that the first card is an ace. Well, it's 4 out of 52, right? There's 4 aces, 52 cards in the deck. But if we know A occurred, there's 51 cards and 1 less ace. So that would be 3 out of 51. So the probability of A and B both occurring is this product. Okay, it would be that product. So that's what we get there. Okay. So that's what happens with the aces. Now, both cards, let's say, were the ace of hearts. Well, hopefully you saw this is going to be 0. Now, why is that? There's only one ace of hearts in the card deck. You can't draw it more than once. It's impossible, right? Because there's only one ace of hearts. Hence, the probability here must be 0. Well, now for red, now both cards being red aces, again, it's really the same idea. Except now, how many red aces are there? Well, you have the ace of hearts and the ace from the suit of diamonds, right? Remember, I did say this, although I guess I could have said it before we did the problem. A card is considered red if it's from the suit of hearts or the suit of diamonds. So let's let A be the event that the first card is a red ace. B is the event the second card is a red ace. Right? Again, there are 2 red aces in the deck, right? So the probability of A here would be 2 out of 52. Now, if we assume A is occurred, so you did draw, right? You did draw, that is, you took out a red ace. There's only one left and one less card. So the probability of B given A would be 1 out of 51. So the probability of A and B is this product, which is equal to this, as you can see. Okay. Again, I know I didn't write in the beginning, that I didn't demonstrate that is why A and B are independent. I know I should have done that, but it's really not hard to see, hopefully. I mean, if you were to calculate the probability of B, given that A has not occurred, right? So we're in the first one now with both cards being hearts. Excuse me. If the first card was not from the suit of hearts, right? So in other words, if you were to find the probability of B given that A has not occurred, well, that means the first card you drew was not from the suit of hearts. I mean, you drew a card, I don't know what it is, but it's not from the suit of hearts. So the probability of B given the complement of A, meaning the probability of B given that A did not occur, that would be 13 out of 51, which is not this. But again, it's really just like the bag of marbles, so the idea is really not that much different. Mostly because we're not putting what we got from the deck, we're not putting it back before we get the second card. All right, excuse me, not there yet. Any questions on these? Okay, I will add to the notes later that showing why the events A and B are independent. Oh, excuse me, not independent. And I'll add later that red cards are cards from the suit of hearts or suit of diamonds. I know I should have added that, and again, I am sorry about that, although I did say it. But anyway, let's move on. Okay, so we handled the probability of and, right? You know, A and B occurring. What about or? In other words, how could we find the probability that events A or B occurs? Now, there is something you have to remember, though, in math. When mathematicians say or allows the possibilities of both. I mean, normally if you say or, for instance, if you say for lunch, I'm going to get McDonald's or Moe's, you know, the Mexican place downtown, you're not saying that you're going to get both for lunch, right? When you say or in everyday language, right? You're not going to, when you say for lunch, I'm going to go to McDonald's or Moe's, you're not saying I'm going to go to both, right? But mathematically, when you say or, both possibilities can occur. So in this case, we do allow the possibility of A and B. Well, the probability of event A or B occurring would be this. It turns out to be this. Essentially, you're going to add the probability of A plus the probability of B. And then you're going to subtract the probability of A and B. Now you might be wondering, why do you subtract? Well, let me say it again. So the probability of events A or B occurring, it's the probability of A plus the probability of B minus the probability of A and B. And you might be thinking, why are we subtracting? We subtract in order to prevent overcounting. In order to prevent overcounting, okay? The next example, I'm going to illustrate that, but let me just pause the recording and fix this. This is driving me nuts. And let me fix this. Sorry about that. I had a spelling mistake.